I would like to congratulate the team from Reddit on their ability to pack a hall. They're going to have to. And they're going to have to stand in the back. It's an SRO crowd. Welcome to the second talk. I've already named their company. We have, now I've forgotten my names because I left my phone over there, Doug, Cliff, and Chris. Thank you, Chris. From Reddit, you may take it away. You have the mic right there.
Hello. Oh, that works. Okay. Hi, everyone. I'm Doug, and intro slide. That's me on the left. You can find my stuff there, my Reddit username, even if you want to DM me. But I'm Software Doug everywhere. Chris is infra guy on our team, and Cliff works on general backend development and helps us with all kinds of things in search. So we're part of roughly the SREL search relevance team at Reddit, and Chris confused me. It's his fault. Chris and I used to work together at Shopify. So, yeah, we're going to talk today about learning to rank, and really what we're going to talk about is we're going to be pretty upfront with a lot of our failures. We're going to talk about sort of how you do this at scale and how you add it to a system that is already mostly working at scale. Of course, at Reddit, we have like thousands of queries per second. We have 19 years of posts. We just have tons of data. So it's not trivial anytime we need to add something. It's a bit of steering a giant cruise liner away from things. And, you know, let's talk a little bit about what Reddit content looks like. So, of course, you might imagine we have a lot of text-heavy informational content. And that's true. We do have a lot of text-heavy informational content. But it's a bit different than just like, you know, normal question answering. We also get a lot of the normal like social network kind of searches. So it's interesting. People come up and they imagine that what we do is always such and such add Reddit. You know, when people add Reddit to their Google search, that we're trying to necessarily replace that. But people do use Reddit search in a different way. They use it for like, what is the latest on this topic, in the same way you might have, you know, go to Twitter or whatever your favorite social network is to kind of see what people are talking about. So recency, popularity is very important. Also really important is just like in this age of AI, we have Reddit is the anti-AI in a lot of ways. It is the subjectivity, the long tail of human experience of like what a specific human being experienced about something. Whereas if you go to ChatGPT, you're going to get sort of a generic Wikipedia tone of answer of something. But you get all the insanity of human beings, a very long tail of like what headphones I liked, or this person looking for help with their golden retriever. You get queries like mental health, like why am I so sad? It really ranges from all kinds of things. And we're in this system, we're trying to solve these problems, and there's lots of things we can do to solve these problems that are a combination. These problems are a combination of normal text retrieval, but also social network and recency. All of these signals are really important to us. We're in the system where this is our sort of like where we're headed, at least the first version of our machine learning-ish search system, whatever we want to call it. And I want to, because I know people will ask about vector search, which is over to the right, but we are on the left. We are talking about LTR with lexical features, the boring old BM25 stuff, and the stuff that is still really important, but not necessarily the cutting edge or bleeding edge of what we're talking about these days. But it's still really important, and it's really important for us to get like fundamentals down for ranking. And we're going to talk about Mr. ML model. Literally, this is a bunch of emojis because I don't believe in clip art anymore. Emojis exist. And Mr. ML model is going to say, I want to improve your search relevance. So how do we do that? First, we need to get training data, right? We need a bunch of like results of like search results, what's relevant, what's not for these queries. Here's a key bridge and like some labeled results. Are these any good? And we need some information to like generalize. So like you've given me examples of what's good or what's not. Why is it good? Why is it bad? Because we're not just repeating training examples. We're trying to basically teach this ML model a skill. Like If you see stuff that looks like this, it is relevant. If you see stuff that doesn't look like this, it is not relevant. So really, modeling in ML space is about generalizing patterns and looking for general patterns. So we need all these features. What was the BM25 score of the title? Did the subreddit match the query at all? What is the title match and the keyword? Did it match 1 or 0? How many hours ago was the post? All of these like notions of things that we know go with relevance. And there's all kinds of things we could theorize about that. And finally, and the part that a lot of us in the data and ML world take for granted is somehow I have to yeet it into production and get it to re-rank results. It turns out that's not as easy as just yeet, and we'll talk about that. And of course, we can easily have a garbage in, garbage out, where if we don't think much about the stuff on the left, we'll just get garbage on the right, right? Mr. ML model is not, it's clippy. Clippy is not going to be, it's not going to be super smart with giving it garbage examples. And if we do amazing things, we can get, you know, we can make amazing search results, right? So it's also not even just about ML. I want to be really clear that a lot of times I think people make the mistake with LTR of like trying to run before they walk and walk before they crawl. But LTR, I always see as a forcing function for increasing the maturity of a team's practices around these. Because we have a tool like Cupid, which I have the t-shirt of, and Cupid's just a manual relevance tuning tool. And a lot of what we gotten over this whole LTR project is not even like that we shipped a model that re-ranks results. It's that we have really good labeled evaluation data, and we have a notion of things that might improve relevance. And we can learn from our model and just add that to our core retrieval too. And that will also drive incremental experiments. So a lot of the times it's the experiments that we found along the way of shipping an ML model that are some of the most impactful things. So I'm going to go through this talk. First, I'm going to talk about training data feature selection. We're going to talk a lot about getting these models into production. And then I'm going to talk about like where we are now and sort of like the painful lessons we've learned and what our next steps are going to be. So Searchbench is our offline evaluation tool, but like this is the graphic I share with the team all the time. That the reason that we need to care about offline evaluation or some of these core practices is because the teeny tiny tip, there's an actual model that we train, but there's this whole foundation of knowing what relevance even means for our team or what corresponds to relevance, what features go with relevance. And really that's just classic relevance work. So what we spent a lot of time doing was making sure that our offline evaluation data, our judgments, as you may have heard, sort of like labeling what's relevant, what's not, actually corresponds to good A/B tests and like points in the right direction, because that's what we're going to train a model on. That's really important. So spent a lot of time just doing manual relevance work with it. And so one thing we did was we have a partner that labeled some search results for us. And we got a bunch of, to start out with, we got a bunch of these queries labeled, about 20 per query, sampled from the head and tail of our distribution. And that in and of itself is useful just as a test set, but more importantly, we sort of learned a formula that goes with that data that we got. So we took that data and we said, okay, what does this correlate with in our analytics? And the thing that we found correlated is this, what internally we call good visit, but is really just a click plus dwell that you may have heard from. And we noticed some other things, like there is like a click is useful, but also, and there's a little bit of position bias in our search results. So things farther down just generally tend to get clicked less, but mostly it's about this click plus dwell. And that was that made us feel really good that like hand labeled results by people outside corresponded with a metric that we use internally as a success metric. So that became the foundation of our judgments, was basically a formula that's sort of a little bit of this blended together. These are just added together and weighted. And then we started to use the judgments. We shipped a lot of A/B tests. Did it go up? We tried a lot of like normal relevance tuning. Is it seeming to improve or not? And we shipped it and checked to make sure our offline and online agree. And okay, this is just boring. It's not really ML, but I I don't care. It improves relevance and it's informed by data, and the model for now is tuned by hand, and eventually it will be tuned by machines. But this is important foundational work to do any ML work, in my opinion. And finally, we would yeet that. Finally, we could take that, if we felt good about the NDCG going up in our manual tuning, and actually train a model and yeet it to production and see if that agrees with online data. One thing, so that's just generally how we got started on training data. One thing that happened when we were doing this work is we also had to do feature extraction. And one trick with feature extraction with LTR is, especially if you're using engagement data, you're always, if you have like this key bridge query, every single thing that got engagement probably matches the text key bridge, because that's just what your current search result shows you. So you do have this like tendency to have a lot of bias in your search results towards these features. So every single feature here may be 1. And think about what that means. If every key bridge feature is 1, I, as a human person doing manual relevance tuning, can easily use my brain and say, oh yeah, well, obviously I want these matches are better. But a model is just going to say this feature is meaningless. Everything is always 1, and I don't have any negative examples. So a really good LTR trick that a lot of people use, and we use this on the Wikipedia project, and I learned it from those people mostly, but also in other projects, is literally just to take a random set of other queries positive labels and just treat them as negative for this label. And this actually works really well, because almost all the time a random document from the index is irrelevant for a query. And we can just have our training set. We don't have to go and do extra extraction from the search engine to pull these features down. We can literally just say, oh, well, I also have this golden retrieval travel anxiety query, and it's irrelevant for these key bridge queries. I'm just going to sample, and we sample like 50, and we slot them in. And that helps our model learn these patterns of negative results when things are obviously irrelevant. So that was a really key learning when we were doing this. Yeah, and now our model can sort of see this pattern of no title match is irrelevant. So it's really important when you're doing LTR to really look to see what your feature balance is and all that stuff. And then finally, we would start with our core features, kind of like the normal stuff that our normal base retrieval ranking is doing with Solr. We use Solr, by the way. I don't think I said that. And we could then ask the question of, how do I know if a feature is good to add to the model? That's always a question. And you can think about this not just in terms of LTR, but in terms of should I index this because for regular retrieval, will it actually add information that isn't already in the index? And if you think about this, you often have what's already in the index might be really strongly correlated. Stuff that matches the title is almost always going to match the body. So the body BM25 doesn't always add much more information on top of the title, because things that are in the title are often always in the body, right? So that's not necessarily for an ML model lots of great new information. But what might be really good information is when there's no correlation. So here we have the number of votes, and obviously the number of votes may have nothing to do with the title BM25 score for a given query. There's going to be good stuff about that topic. There's going to be bad stuff about that topic. And so these are not correlated at all. And think about what that means to a model. If you add this to a model, it's a new signal that has nothing to do with your existing signals. And suddenly you can make a decision. If NDCG goes up when your model or your test train split, your quality goes up, you can pretty strongly attribute it to that feature as being a cause of that. And we actually would do this this is a subset of our features doing correlation. So we can see each feature correlating with each other. This is just a correlation matrix. And what's interesting is you can see on the bottom left, and you can see the diagonal, obviously everything is correlated with itself very strongly. On the bottom left, we have these zones of the vote count, the comments count, how old something is. And you can see how those things actually kind of correlate, but they don't correlate with these other features that are BM25 features. So it's adding information on top of those. So we spent time analyzing which features when we add them. And then, of course, when we add features to the model, this is just a simple pairwise classification of relevant and irrelevant. It's not even what we necessarily put into production, but we can see, oh, this improved. It seems like this model is reasonable and useful to add, or this feature is useful to add to the index. And finally, I'll just mention the model architecture. I think model architecture is sometimes interesting, but also it's getting all these practices right is often more important. But we actually have a deep learning model that just because it's important, these things are important to your model architecture. You're optimizing a list-wise thing like a ranking getting right. That's a fundamental difference between learning to rank and non-learning to rank ML. And then you have to sort of handle the fact that a lot of features will you just have to be resilient to correlated features. Not all model architectures can do that very well. And there's nonlinear relationships between things. Often it's like, if this query seems to be about a recent topic, then these ranking signals matter more. Otherwise, it may be that there's just informational thing and I want to know the best headphones, and that's a longer tail thing. So relevance is not one formula. It's a very nonlinear if-then branching situation. So that's why a lot of gradient, you see a lot of tree-based models. So we're using a lambda mart loss, which is, you can go learn about it. There's a bunch of blog articles. You can search on softwaredoug.com. Actually, you can't search on softwaredoug.com, but you can go to Google and search for softwaredoug.com and look for lambda mart for a great notebook on that. But we actually are using a deep learning model with that loss function. So with that quick tour, I'm going to turn things over and we're going to talk about getting things do the yeeting part into production. So.
Awesome. Thanks, Doug. So how do we get LTR at Reddit off the ground? So at Reddit, we use Solr. So naturally, we want to consider Solr's native LTR plugin, which can handle both feature calculation and model inference to re-rank the top end results. However, we also had the option of re-ranking outside of Solr with Reddit's existing ML infrastructure. We had a lot of criteria to consider when deciding if we wanted to use the LTR plugin. Ultimately, we focused on query-dependent features and time horizon of content as the main reasons for picking Solr LTR. It was important for us to get something out the door quickly, and having feature calculation and model inference together natively in a plugin was really appealing. So what does this look like under the hood? The configuration consists of JSON that specifies where our feature store lives, and most importantly, what this feature looks like in Solr query syntax. For our first pass, we picked straightforward features like title PM25, comments count, self-text match, that kind of stuff. For model training, we sent samples of our query stream against the Solr LTR cluster for feature logging. And once the model was trained, we deployed it as a config update and rolled it out to the entire cluster. For inference, we added an extra re-rank RQ parameter to our Solr query to invoke the LTR plugin. This tells Solr to re-rank the top end results after the initial retrieval. So now that we've run through the details of what's happening under the hood, let's take a step back to see what the entire system and testing looks like. This is a simplified view of what our request flow looks like. Our query traffic is passed through a microservice, which handles things like normalization, filters, and now re-ranking, before forwarding the request to our Solr cluster. Before we begin any kind of testing at scale, we need to answer one question. Should we re-rank traffic in the same cluster where we handle non-re-rank production traffic, or should we spin up a separate cluster and do the re-ranking there in isolation? We asked ourselves, what are the most important sticking points for that decision? We could jumpstart the project by using a single cluster, which we already had, which would give us an accurate read on latency and also allow us to presumably vertically scale out of any performance problems we see. On the other hand, this would slow down development by forcing us to coordinate our changes with non-LTR work, which would be a headache. We would also risk taking down the entire prod cluster if we had issues with re-ranking if we used a single cluster. So naturally, we decided to use a single cluster. Hindsight is 20/20, but at the time, we thought latency and dollar cost were the most important things to get right. Spoiler alert, it turns out safety and development isolation are much more important. But we'll get to that shortly. So our first attempt at productionalizing LTR at Reddit prioritized latency and dollar cost by using a single cluster. We really wanted to make sure that the latency readouts we're testing would accurately reflect what we would see with production scale pressure and traffic flowing through the cluster. However, we also wanted to test LTR without returning suboptimal results to users. We knew our first few attempts would be far from perfect, so we needed a way to decouple these concerns and test freely without worrying about damaging our top-line metrics. To facilitate this, we started using a technology typically used for service-level proxying for shadow traffic through the system. And that looks something like this. So we've been using Envoy as our application proxy layer at Reddit, which felt like the perfect tool to use for mirroring traffic. We set up a mirror policy that would duplicate our query traffic and forward this to a separate set of shadow Kubernetes pods. These pods would talk to the same Solr cluster, which would perform the re-ranking. The main benefit of this approach is the responses from the shadow pods would be thrown away, so the end user experience would not be impacted while we continued our testing. However, once we began dialing up shadow traffic, we began running into large latency increases, which led to down replicas, down shards, and widespread cascading failures. This kills the Solr. So, once we recovered, we made the decision to create a separate cluster specifically for LTR to focus on safety development isolation instead. We accepted there would be a delta between latencies across the two clusters, which we would deal with later during analysis. This would also allow us to safely tune things like the thread module and GC settings without impacting non-LTR workflows. Once our shadow traffic testing looked good, we moved to A/B user testing, splitting a percentage of incoming traffic for re-ranking. And now I'll hand it over to Chris, who will talk about some of the problems with scaling.
Thanks. So yeah, once we started actually dialing up our shadow traffic, things were not smooth. There'll be a slide, don't worry.
Empty space.
Focus on me. And yes, we killed Solr a few times, so we had to do some tuning, which I'll go over. So to give you a little more context, I'm actually curious. I want to poll the room. How many people here are running Solr? Oh, a fair number of people in the audience. So you may have experienced some of the same things that we have. So Reddit operates Solr clusters, to just give you some background on what we're running, that receive hundreds to thousands of queries per second, and we index new documents in real time. Solr, as many of you know, it's a Java-based search engine that needs its Java virtual machine garbage collection tuned quite well to be able to perform at scale, especially when you're serving near real-time traffic. And for those not familiar, garbage collection is the process of reclaiming previously used memory to be used again, something applications should do frequently, but quickly, so that it doesn't impact other important work, like, say, handling queries. And this is a bit of foreshadowing to what one of our problems was. And to handle our scale, we configured garbage collection, GC, and Solr to run fairly smoothly. One of the first things we ran into was the old generation would often grow too large and start starving the JVM's ability to create short-lived objects, which are what you need when you're serving lots of queries, lots of ephemeral work. Unfortunately, those changes didn't fully fix our stability issues on our cluster. We were serving re-ranking traffic with the LTR plugin. And to understand why, I'll go a little bit more into background on how LTR works. It's first, it's going to issue the actual query that we want to get for retrieval, get the top-end documents that are relevant per shard, and then we're re-ranking all these documents in a second pass, issuing even more queries to compute some ML features, which we're then sending to Mr. ML model. And then we're going to return your re-ranked documents. And remember that our challenge is to try to get this to run on thousands of queries per second, dozens of features, 19 years, billions and billions of posts, and to do this without Solr falling over. And it did many, many times, and I'll take you through one specific example of how it did. So normally on our clusters that we're not running re-ranking on for Solr, when we increase traffic, this is just a look at the total number of requests that are being handled by one of our clusters. When we increase traffic slowly, we'd see some stress that's indicated by slightly increased garbage collection pause times, frequency, and some slightly higher query latencies. But usually, the Solr nodes stay online. The follower nodes would keep up with the updates from their leaders, and the cluster would generally be reliable. With LTR, not so much. Every time we started to ramp up traffic on the cluster, it would invariably enter a death spiral, wherein And here I'm showing garbage collection, the amount of time spent doing garbage collection per node. The amount of pause time would increase rapidly to a point where it was taking too long garbage collecting, so it's not doing enough other work, like say serving queries. The follower nodes would then get too far behind their leaders, and they realize, oh, we missed some updates. We need to start replicating, which would add even more work to that poor JVM, which is trying to run this. During which GC times would again, of course, increase because of that. And we would repeat this cycle until individual nodes and then whole shards were down. We were not able to serve traffic, and we'd have to press F to pay respects and intervene manually to try to get those nodes back online. So we had to do some thinking. So to try to figure out what was actually going on, we wanted to look a little bit closer at a smaller increase in traffic. Let's not just ramp all the way. Let's just look at like a 5 to 10% bump in traffic and look deeper at the effects. We noticed that we had a disproportionate jump in the average amount of time we're spending garbage collecting just by doubling that traffic from 5 to 10%. We got 3 times as much time spent garbage collecting. Not ideal. Worse yet, that increase in time was spent and the frequency wasn't stable. It was slowly increasing, which would invariably cause that death spiral that I mentioned earlier. It looked like we had issues with GC throughput, and we wanted to try to fix this quickly during this project. We wanted to get it off the ground, so we tried throwing nodes at it. We tried vertically and horizontally scaling to no avail, but realizing that we need to look at some other performance optimization techniques. Critically, the most important one is we asked in what way can we do less work? Or put another way, can we put less load on garbage collection? We dove into what was different about this cluster. Re-ranking. Are the clusters working pretty fine? What extra work is this doing? We focused on the LTR features themselves. We know this cluster runs well with ranking turned off. Are some of our re-ranking features that we're calculating during query time, are they a little too expensive? And we started to compare this cluster to some of our other clusters and noticed that in particular, one of the filter cache specifically seemed to be something that looked quite a bit different. People say that the internet is a series of tubes. No, it's actually a bunch of caches, including this one, which is very important to try to keep Solr actually performing well. The filter cache just stores filters that have previously been used so that it doesn't have to go back to disk or back to, it's in more efficient memory structures, but for being able to use at query time. And when we increased our re-ranking traffic, we saw that the amount of items in the filter cache, which is on the far right, that kind of green line, that just ballooned astronomically. We also saw that there was a fairly high, on the left-hand side, a fairly high number of misses, cache misses that were occurring. And we're getting about a 3x jump in the amount of items that we're putting in that filter cache for twice the traffic. And all of this is, we began to suspect, is maybe just putting a lot of short-lived items in that cache that then need to be garbage collected. Taking a look at the actual hit rate for that cache, it was at about 75% on average for the Learning to Rank plugin, and we get around 86% without the Learning to Rank plugin, which is 10% different, which is fairly significant in terms of performance. Then we wanted to, so knowing now that maybe this is something we should suspect, we wanted to take a look at what is the LTR plugin actually doing itself internally. So we dove into both the features that we're using and some of the code. Here's one of the features that we use when we're re-ranking a query. And remember that we're going to be so in this case the queries themselves are fairly simple, but because they're for specific documents in a document set, they're maybe not going to be fairly reusable, we saw in the code. So it does look like this is going to fill up our cache with a bunch of items that are going to be just a filter cache with a bunch of items that are going to be evicted later. Specifically, we have some features that, not all of our features do filter queries, but this is an example of one of them that does. And in our case, we have 46, we issue 46 Solr queries per query. 6 of them are filter queries like this. So we have the potential to add a lot of different things into that cache. And we weren't quite sure, is this plugin actually caching this information? We dug into the code itself and found that yes, actually it calls a method called getDocSet, which the Javadoc description reads, if the answer is not cached, it may have been inserted into the cache as a result of this call because it's cache aware. So we strongly suspected that yes, it was these features were perhaps a little bit more expensive than we wanted. They were making filter query calls, or queries with filter queries in them, and probably evicting a lot of those in the cache and causing a lot of pressure on garbage collection and our long GC pause times. But the issue could have also just been the 46 other queries that we're issuing per query, or just any of the filter queries that are used in the as the actual query itself. Any of those could have been the actual issue. So we thought, let's try to design an experiment to test what is truly the issue here. So we thought, let's try a few different variations of how we're doing re-ranking. Let's do exactly what we were doing before. So re-ranking with all of our features. We know this is going to cause some high GC. And we're going to try just turning it off entirely, issuing the query itself, but no actual re-ranking. Then we're going to try re-ranking, but we're going to omit what we think is the issue, those filter queries in our features. But we kind of want those features to use those. So we're going to try a 4th variant as well, one where we are re-ranking, but we're specifically telling Solr to not cache those queries. So trying this out, we've got another diagram of our garbage collection with time on the x-axis. We observed that there was a fairly large difference between these. Starting off, we kind of ramped up our traffic from 5 to 10%, and we observed our high GC times again, increasing to the point where we would enter our death spiral. We saw just turning off re-ranking, our GC times plummeted to really nice low levels. Awesome. There was a short bump in GC time when we changed our configuration to prepare for the next 2 tests. We then looked at trying out those 2 other variants. We tried using turning on LTR again, but using none of the filtered query features. And we saw there was a jump in garbage collection, but not as high and not as well shown here, but crucially, it was not increasing. It was a stable amount of garbage collection. So we thought, hey, awesome. Maybe we confirmed that these are going to be the issue. But we still want those features. So we tried the version that specifically says, run the filtered queries, but just don't cache the results. And the result was quite similar in terms of garbage collection, which was great news. It means we could probably use those features still. Just they need to stay out of the filter cache. And how did that actually affect the filter cache itself? Well, here we can see on our far right side the amount of items that we were putting into it. Again, when we were doing the normal, just turning our regular LTR on, ballooned exactly as we expected. Turning it off, started to empty the amount of items in that cache, also as expected. But we thankfully nicely saw that we didn't build up massive amounts of items in that cache when we were not using the features at all, no FQ, or when we told it specifically to not cache, which was great. Also, in the version we showed without caching, our searcher warm-up time was thankfully stayed nice and low. And you can probably see there was a massive drop in the number of misses in the filter query cache. We also found that our hit rate increased when we did this because it looks like not a lot of the items in the filter cache that were being inserted by LTR were particularly useful. They were dragging down the average hit rate by quite a bit. So we are now able to get 95% hit rate, exceeding even our other cluster at the time. And throughout all this, we're even able to get pretty decent latency. Those garbage collection times, how those often show up to users is what you can see between the on when we started to ramp traffic and the offside. Occasionally you'll get longer spikes in latency when we have to stop the world in some cases. That occurred when we were throwing things in that filter cache later on, except for the part where we changed configs. no massive latency spikes. So with those results in hand, we were pretty confident that we could be able to start adding more load to this cluster, and we solved just one of the many reasons why our Solr clusters were failing. So specifically for just for some info things, some takeaways for near real-time query indexing in Solr, GC performance, both its throughput and latency, is incredibly important for stability. And when optimizing performance, try to look at what you can avoid doing, try to remove some work, look at you. And for the learning to ring plugin in specific, or in other machine learning, if you're doing things online, look at the cost of your features as they're being computed and the potential effects on both intermediate, like the filter cache, or transitive dependencies, like the JVM GC, and see what could be, how those could be affecting things. And maybe you'll have more success than us initially. And I'll pass back to Doug to now talk about next steps.
Now that we're yeeting to the moon, yeah, so we started to really ramp up our A/B testing flow through this year, as you can see those dates there. And I feel like every LTR talk, especially a real LTR talk, has like something like this, where you kind of like get to a baseline where it's sort of maybe better, but really it's neutral and it's not significant. It's like the plateau of despair. So we got to a point where offline said some of these should be better than our baseline. And it turned out not to be true. And we did a lot of soul searching around this. And one thing that really the main takeaway, another big LTR takeaway, when you're doing manual relevance work, you're sort of like even subconsciously doing a lot of LGTM, looks good to me. Even if you're 80% guided by NDCG improvements, you're like, well, that's still pretty good. I think that's better. The team likes these results better. I'm going to put it into an A/B test. When you're doing Mr. ML is pretty stupid. It's just like taking in the training data and like trying to make ranking better, right? You're giving it tons of examples in bulk, and those examples better be spot on. And the other thing, the examples need to be weighed by frequency. Whereas when I'm doing like my manual tuning and be like, well, here's what it looks like on head queries. Here's how it looks like on tail queries. It seems neutral here, or better here, or let's ship it and see what happens. But when I'm doing training, it's like, I really need to get these very frequent queries right. And these tail queries, maybe a little bit less important and so on, so that will result in certain A/B test outcomes. So we did a lot of soul searching. And the other thing that really came up that you might think about if you're like going Google, one thing that social search has that I think a lot of search doesn't, the SERPs really change a lot. So often when we're dealing with training data in other contexts, I can like aggregate 30, 60 days of clicks or whatever, and reconstruct what a typical SERP looks like by like just saying like sorting by the judgments and saying like what was most relevant over the last 30 days. That doesn't really work in social search. Everything is changing all the time, very fast, and we would have some queries that would have like 1,000 different results, unique posts coming in for like a query like, you know, a prominent politician or something, just like constantly changing because people are always posting news about that topic. And that's a bit different than like even e-commerce search. Sometimes your SERP might change a little bit, but it's not going to change so much. And you think about this, like this is the typical way that people get this stuff. They'll have a click model or something, which is just taking these specific individual search interactions and sort of like averaging them or aggregating them over some days, and then turning that into a label that's then trained on. And this works actually in like, I would say a lot of search applications. Where we're running into problems is like just how much these change, and just aggregation is hard to do over a meaningful amount of time. So we're getting away from that. This is like all future work. And what we really want to do is get away from using some synthesized label to just like taking the SERPs directly, the search result pages directly, and getting the features for that exact occurrence, appending those to the right of this thing for each search result, and treating that as a single training example. So as someone searches and we know what the vote count of the votes were, or how many comments something got, what the title BM25 of that time, We're going to put that all in our data warehouse, make that a training example, and just train directly on that instead of trying to do any click modeling. It's a lot more data, and we need to think about doing feature extraction every time a search happens. So those are some downsides. The other nice thing about this is there's a lot more context on these rows. We have the user ID. We have the date something happened on. We know that a search happening in this very specific context with these very specific features results in these things being clicked or not clicked. So we're moving maybe to this sort of notion of our training data. The other thing is, so we have this notion, you may have heard, especially if you've read AI-powered search or have familiarity with like anything from LucidWorks or anything, there's a notion of signals, and signals sometimes is an overloaded term. But in this case, signals refers to things that we know historically have tended to perform well for a given query. One thing that we learned, our initial plan was LTR is going to be applied to the long tail of search results that don't have signals. If it has signals, we feel like we're just going to ignore that, at least for now, and like let the signals take over. And we learned that signals actually cover something like upwards of 75% plus of the search interactions, which was a big surprise to us. And so we sort of have to figure out a plan for incorporating this data of like what has gotten recently, so usually relatively recently, getting back to that dynamic SERP notion, what has been engaged with recently for these posts. And you could think about signals as like, it's actually like an overfit, just a bunch of labels of like memorizing what was good at one point. We of course want the model to sort of generalize. So it's a bit of a tricky thing to get right, because if we just give it signals, it's sort of like letting the model cheat. So we have to sort of balance out when we hold out signals and when we give the model signals when we're training, so that it can like learn general patterns that aren't just like memorize stuff on the left of what's signals. Yeah, like I said, that covers way more. So yeah, we're going to be next up. This is actually hopefully the next round of A/B tests. Is to train with signals in addition to our core retrieval, and get the ideal mix of signals and lexical as our next model. And that's it. So yeah, thank you. I want to mention, by the way, quick plug. I forgot to put a slide for this. The book that Trey, that I've been helping with Trey, AI-powered search, is going to be coming out soon. I put a discount code for that. If you want to learn about learning to rank, there's a lot of great content there, but also signal boosting and lots of other stuff. So check out AI-powered search. So.
All right, and we have 30 seconds for questions. But 15 minutes until the next talk, so there is an opportunity for numerous questions as long as I don't start with Stavros.
On your very first slide,
And the mic, the Zoom people have to hear.
right, on the first slide, or one of the first slides, you have the model where you do the LTR on the lexical features, and you have the vector on the right. Why is the vector score not an input to the LTR? Why is it not a feature in the LTR?
Yeah, that's something we hope to do in the future, definitely. It's just, we have like the other thing that we didn't mention, we could potentially be doing inference at different levels too for our model. So there's sort of, we could have a base ranker, and then later farther down, we might have a ranker that sort of figures out how to combine these things. But you're totally right. That totally could be a thing. There's no reason not to.
Thanks. Hi, this is maybe just more of a clarification. When you were talking about the training data, I might have just missed because of lack of familiarity, but you talked about giving what I understood to be like counter examples of irrelevant queries. Would you mind just kind of recapping that again a bit? 'Cause was it basically like for a given query, you give examples of like a query that doesn't work?
Yeah, it's within a query, actually, results that are irrelevant. So sometimes you have just, so we have results that are irrelevant, but they also match the title. Sometimes that happens, right? So if you look at that, if you're a model and you have to make a decision, how do I use title match without that? You won't use title match to decide whether a result is relevant. because there's nothing there. There's no decision to be made, right? You can't say if you just see this data, if you see a table of data, a model can't learn that title match for this key bridge query matters. But if we inject some various noise in there and some different things from other queries, it can really learn that pattern. And that was something that really improved our model performance early on.
So it's already on a per feature basis.
Yeah, per feature.
Feature of title match.
Exactly. Yeah, and we're not smart enough to like make sure it's balanced and everything. It's more like we just randomly pick some 50 things from other queries and stick them in there, and it helps. But yeah, we could probably be more intelligent in looking at the balance of features and making sure we have representation over all the labels.
Coming from Habib Shupeju, I'm curious how long it took them to get the tuning issues right and what they used for observability that helped in figuring this out.
We are still working on some issues, so it's still ongoing. But we've come fairly far. It's probably that we unfortunately tried to do a migration from Solr 7 to Solr 9, and also from running on just EC2 to Kubernetes at the same time as also trying to tune LTR. We've been dealing with a lot of stuff, so it's still ongoing. But we use Grafana internally to try to do a lot of visualization, and we've got a lot of people writing a lot of good queries and visualizations to try to figure out to diagnose things.
Do you guys ever see like having like a model fine-tune automatically, or do you think it always has to have like a human in the loop as part of the process of like fine-tuning the LTR models?
Yeah, that's a good question. Eventually, I feel like it's good to start with the human in the loop and like gradually relax. Right now, we very much have a human in the loop. But especially as we get to retraining, there's a whole topic of model monitoring and like making sure your model's not doing weird things, where it becomes more about like almost like monitoring a production system to make sure it's not going off the rails. We're not at that point yet, but if we train models like weekly or something, we'd want to like not so much like have a human approve everything, but more like have monitoring in place and observability to know when things are like not good and we should roll back to last week's model or something.
And question from Aruna Govindaraju. A generic question on the LTR plugin. How does number of feature sets affect latency and performance, and how can we improve combine?
So you can play with a number of threads that the LTR model is able to use, and you can give as many cores as you like to the JVM in that case. So playing with those settings can let you can help improve latency with various models. In terms of the number of features though, and how that affects things, I don't know, you may have more insight.
Yeah, just really quickly, like one thing that Cliff and I spent a lot of time doing early on was we would test turning features on and off and trying different scenarios to on latency, and we did find some unexpectedly expensive features and took those out. But it's only going to be like it's literally the same as if you ran the query directly to Solr. And so I often tell people say, well, why is my LTR slow? And the most important thing is I think it's good to actually take the features out of the LTR plugin and just run them as queries directly to Solr and see what's expensive. We found that like things like re-rank depth or the model wasn't necessarily that huge. Of course, if you get like re-rank depth of 1,000, it can really impact things. But what really impacted things was like weird features or like, you know, this filter query thing or whatever.
And final question from Mike Henderson. Where can I find the discount code? Say that again, please.
The search relevance Slack, opensourceconnections.com/Slack. And there is a discount code in there. So check out AI powered search. What's that?
The Haystack conference channel.
Oh, it's in Haystack conference. Yeah. That's what I get for typing it in the middle of my colleagues giving a talk.
Thank you all very much. Let's thank our speakers again.